Yesterday we have done confidence interval on population proportion with sigma known and sigma unknown. There's one subtopic from that section that I will cover later on, but I think I will do 9.1 first. Then after that, we will go on talking about that subtopic. 9.1 is on confidence interval for population proportion P. The idea is still the same template. The template was, you know what? Let me quote it from yesterday. From yesterday, it's my template. Template is here. Give me a second. I will quote these. The template will be like this. This is our template yesterday. Okay, now then when it comes to P, then we do modification here. Now the best point estimate will be P hat. That is sample proportion. And another modification, so what happened is we don't use this anymore. The critical value is still the same though, okay? Critical value is still the same. Now another modification is here. Another modification is that the sigma is now replaced by square root of P hat Q hat. Now, such that the margin of error is critical value times square root of P hat Q hat over square root of n, which we then usually just write it this way. P hat, square root of P hat Q hat over n. Now, of course, because of that modification, then another place where it will change is this part here. Now, it's not X bar anymore. It's not X bar anymore, but it will be P hat minus margin of error less than P hat plus margin of error. Okay, that's another place where it will change, but that's simply because of the parameters being changed though. Okay, let me use yellow instead. Okay, that's for the template. That's for the template. We will do exercise right away, very soon, but some requirement. Note, requirement to use this model. According to our textbook, the requirement is that n times P hat times Q hat should be at least 10 or more than 10. That's a question mark there. I don't remember precisely. You can say this means the sample variance, if you remember the variance of binomial distribution, that's NPQ, right? Yeah, but because we have P hat, Q hat, then sample variance should be more than 10. That's what they say. And there's another one requirement from our textbook. Another one requirement from our textbook is that the sample size should be less than equal to or at most 5% of the population size. But I want to say that this last requirement here is strange. And not required in general. Okay, now why do I say strange? Why do I say strange? We know that the larger the sample size, the better. The larger the sample size, the better. But according to this requirement, your sample size cannot be too big. And that's why I say it's strange. We know that the larger the sample size, the better. But according to this textbook here, they say that the sample size cannot be more than 5% of the population size, which, as I know, is not true. Okay, at least that's not what being required in other places. Like from what I read, what I read before, that's not really being required. Okay, now in fact, the requirement that the sample variance should be at least 10 is way too strict. This is way too strict. This is way too strict. Because, so what happened is this. To have the sample variance to be at least 10, usually your sample size has to be very big. Okay, and with some computation later on, you will see that N will be at least 40. Yeah, N will be at least 40. But at the same time, your N cannot be too big. So if your sample size is, let me show you the little computation in case, but you don't need to really understand this one though. Quite heavy algebra. So N, P hat, Q hat is at least 10, right? Now let's decipher this. What does it mean? Now you will see that P hat, Q hat is actually at most 0.25. And I will explain it much later why this is true. P hat, Q hat is at most 0.25. Now, if P hat, Q hat is at most 0.25, that will bring the situation that the N has to be at least 40, even in the best scenario. Even in the best scenario. While at the same time, if N is at least 0.05 of this N, then the population size should be at least, population size will be together with this. And the population size should be times 20. That would be at least 800. But the main problem is actually this restriction here, because somehow we should feel strange that they put restriction on the sample size, that there's at some point your sample size is too big, therefore the model is not reliable. What kind of model is that? While we know that if you read section 8.2, as I remember, this model also relies at the same time on central limit theorem. Therefore, the larger the sample size, the better it will be. Okay, so here's the thing. Even though the textbook require us to use these two things, okay, but we will only apply the first one. Okay, we will not use the second one. We will not use the second one. I want to cross something out. Okay, we will not use the second one. Okay, we will not, at least we will not require that. I believe that our textbook will then give us examples that satisfy both of them. Yeah, but that's textbook, right? Okay, in reality, that's not the case. In fact, in reality, most of the times, our population size is very, very big, so it never become an issue. Okay, second, it still feels strange that they put restriction on the sample size. There's a maximum sample size you can use. What kind of restriction is that? Yeah, what kind of restriction is that? Okay, no, there's no, you can't do that. You cannot use that. Now, now let me tell you the common restriction being used. Commonly, not so strict requirement is being used. Requirement is used. That is, NP had at least 5, NQ had at least 5. No, but if N is the sample size and P hat is the proportion of success, then we can say this is the number of successes. Usually we use X when we did binomial distribution. The number of successes is at least 5, and the number of fails is at least 5. Okay, so in practice, that's the one usually used. Now, why do we need this both requirement here? We need this both requirement here, either this one or this one here. That's because we want to have, we simply need to have enough normality. Basically, for us to use central limit theorem and reach that normal distribution shape, okay, then we need the situation that the number of successes and the number of fails at least 5. If you read your textbook, if you have a chance, maybe browse through your textbook a little bit, you will see that the binomial distribution eventually mimic normal distribution. Okay, eventually mimic normal distribution. Not precisely, but eventually, right? Okay, and then of course, the larger the sample size, the better the normal distribution, the closer it resembles normal distribution. Now, but they want to have this restriction such that we don't have, we still keep the symmetry. So what you don't want to have is a situation where the normal distribution looks like this. This is skewed to the right. Okay. While we want to make sure that the number of failures, the number of successes, or the number of failures is not too much, too skewed to the left or too skewed to the right. Okay, so yes, that's what I meant by we need that restriction to have enough normality. Okay, but again, in general, what we check is only this. In practice, that's what we check. Now, theoretically, that's what they want. Okay, the textbook requirement is a lot stricter, while the practical requirement is not that strict, but still we can estimate the confidence interval well enough. Okay, those are the restrictions. So you will see that when I use textbook exercise, when you use textbook exercise, when you check this requirement here, you will be fine. Okay, but every time this is okay, this will also be okay. You see what I mean? Let me show you. Again, this is some algebra. This is some algebra. So if you get it, great. If you don't get it, fine. I know some of you may get it. Notice that NP hat Q hat at least 10. Now Q hat or P hat is a very small number, very big number, right? Okay. So this guy is at least one, at most one, at least 0. Okay. Now, if Q is 1, if Q had very close to 1, close to 1, that means NPQ is greater equals to 10. Right? Now, if Q hat is close to 0, then, and imagine this, let's say Q hat is 0.1, okay? So this is 0.1. Then consequently, NP hat will be at least 100, right? So basically, I'm trying to say that under any situation of Q hat, NP will be at least 10, therefore at least 5. Now the same logic if you apply to P hat. Okay, if P hat is closer to 1, if P hat is closer to 1, then NQ hat automatically at least 10. Right? But if P hat is closer to 0, then you can use the same mechanism here to show that therefore NQ hat is at least 100. Okay? Therefore, as long as this variance requirement being satisfied, as long as this variance is at least 10 being satisfied, then automatically this being satisfied. Okay? Automatically this being satisfied. But there are cases where this requirement is not being satisfied. This requirement being satisfied, yet the variance is not satisfied. That's why I say that this is stricter. The textbook requirement is stricter. Okay, but practical requirement is not as strict. But still, it's actually usable. Okay, the larger the sample size, the better. That's the key. Okay, so what happens if you don't satisfy this requirement? Then increase your sample size. But Thomas, according to our textbook, there's an upper limit on upper fence on how many sample size we can use. Ignore that one. Okay, I'm sorry, but that itself smells strange. It's like I usually use this. Like if you want to know somebody more, increase the sample size, right? Okay, so you need to date that person for a longer time. Okay, yeah, of course you don't want to date somebody for 10 years. That's a jerk. I'm sorry, but yes. If you don't have any plan to marry that person in once you know that that person matched you, don't keep on demanding larger sample size, of course, right? But if somebody really insists that, you know what, after dating you for 5 years, I still think that there's some adjustment need to be done, and both of you agree on that, why not? Just go on, okay? Yeah, if both of you agree to keep on dating, fine, you know, right? But nothing wrong with that, though. Okay, so increasing the sample size is never wrong, not in statistics. So when I read this requirement, I feel something smelly. Yeah, something smelly. Yeah, imagine if somebody say that the election should the election turnout rate should be at least how many people supposed to go to vote, but if too many people vote, then it will invalidate the election. Have you ever heard that? Like the election becomes invalidated because the number of voters is too many. That's wrong, right? Yeah, of course, yeah, I understand if we say that the voters, we have some invalid votes actually going in, like people who are not supposed to vote, like my wife, she's not a citizen yet, so she's not supposed to vote. If she end up voting and too many such case, then yes, that's election fraud, right? But if simply because a lot of people voting, there's nothing wrong with that. Okay, nothing wrong with that. The election fraud is the issue, but the number of voters cannot be the issue. The more people voting, the better. You never say that the election get invalidated because the number of people voting is too many. No, that's I'm sorry, that sounds so wrong. Okay, well, anyway, so that's to address this issue here, the one that I cross in red here. Okay, so that's a question that's questionable. Strange and, oh, you know what? I think strange and not required in general. Not required in general. Okay, let me go on with exercise from our textbook. I will do some standard situation first. Suppose I pick, hold on. Yeah, let me do this. For example, construct 90% confidence interval for P if the sample size, let's say 300, and the number of people who agree to a proposal, let's say is 100. Now, notice that this one is, if you use the less strict requirement, it's actually quite easy to check that you see that the P hat will be X over N, which is 100 over 300. That's 1/3, right? Okay, now check the requirement. NP hat, but NP hat is basically X. Do you see that? Right? That's 100. So you see the number of people say yes to that proposal is already at least 5. And of course, NQ hat, you will see that's basically N minus X, right? So if 100 say yes, then the remaining 200 must say no. Okay, so you see that this requirement is actually easy to see. Okay, easy to see. NP will be basically X, NP hat. NQ hat, basically the remaining. Okay, so yes, we have at least 5 people. At least 5 people say yes, at least 5 people say no, then we can use this model. That's based on less restricted case. Now, but suppose I check using a more restricted situation, then NP hat Q hat equals to 300 times 1/3 times 2/3. Right? So this is 100 times 2/3. That's at least 66.6. But that's definitely more than 5. Okay, that's what I said, that the example given by our textbook and the one I pick up here is actually still okay. Now, then how to construct the confidence interval. Step 1, best point estimate, just like before. Then P hat equals to 1/3. We computed earlier. Let me redo it again. 100 over 300. That's 1/3. You can make it decimal if you like. Let me make it decimal. 0.33333. Now, consequently, then Q hat will be 1 minus that. 0.66667. Now then critical value, just like before, C critical. Now you do your curve yourself. Inverse norm of 0.9501. I think 1.644, 605 something, 604 something. 64485. And step 2, the margin of error, that will be 1.64485 times square root of P hat Q hat over the sample size 300. Okay, now let me show you how to use your calculator in this case. You need to actually, when you have square root and some operation inside, you need to be a bit careful with the parentheses, you know, and different calculator applies different style of parentheses. But with the assumption that you use TI-84, then I can teach you more uniformly. Let's see the screen here. Now, what I will do is I will punch 1.64485 times the square root. Now, notice that the square root here, they put it under, if you use TI-83, it will be square root with parentheses. But TI-84, it will be just square root, but that it's all under square root notation. Okay, and this will be 0.33333. So you see, I hope you can see that this 0.3333 is still under square root times 0.66667 divided by 300. Okay. In this part here, especially because we are dealing with proportion, so the proportion will be between 0 to 1, right? Okay, then the margin of error will get even smaller. So what's that? 0.04 something. 0.04477. 477. Okay, and then declaration, just like before, 90% confidence interval for population proportion will be the best point estimate minus the margin of error less than P less than best point estimate plus margin of error. Okay. From there, then you go on using your calculator. The 0.33333 minus 0.04477, I get 0.28856 less than P less than 0.33333 plus 0.04477. So that will be 0.37810. So we are 90% confident that the population proportion so this is the sample of size 300. Okay, so among 300 people, let's say I put some story in here. Let's say I put some story in here. Okay, let's say of these 300 people, 100 of them say they will vote for Trump. Okay, now then uh, is it possible that actually the proportion of people vote for Trump is higher than that or lower than that 1/3? Then according to our model here, we are 90% confidence that the actual proportion of our population actually will vote for Trump is at least 28 point, approximately 28.9%, okay, but at most 37.8%, okay. But Thomas, this model may be wrong. Yes, this model may be wrong. However, the chance this model to be wrong is actually quite small. Okay, in this case, we can say, even though that's incorrect, not totally correct, we can say that there's only 10% chance to be wrong. Okay, now you can then increase, if you say, Thomas, I want to be a lot more confident, then you go try, change this into 99% if you want, and see what happens. If you make it 99% here, then of course the C-score will get higher, right? Let's just try to see. So if I change this to 99% here, then you will see the C critical later on will be 2.57583. 57583, as I remember. Okay, so this number here, you see 1.6 and 2.5. This 2.5 is not even 2 times of that. Okay, so later on, this will be at most 0.08, by the way. I'm sorry, right? But if you have at most 0.08, then 0.33333 minus 0.08, 0.33333 plus 0.08, it is still much less than 50%. It's less than, it's approximately 0.41, right? So even if you increase that to 99% confidence level, therefore making the interval a lot larger, okay, but however large it's that, it's still less than 50%. Okay, so try to picture this in election. I use Trump and presidential election as an example because I assume that it's you can picture that right away. Okay, you can say that Imagine Thomas applied to be the want to get elected to be the city mayor. Okay, for example, but you know it's hard to imagine that case, right? Okay, so in this situation, then will Trump even try to fight for this city or for this county or for this state? The answer is no, he won't fight for this. Why? It will be a waste of money, waste of time, waste of effort, and in this case, in this situation, maybe more COVID cases, right? Okay, so will Trump ever come to this kind of state? Maybe, but if he comes, it's not campaigning, very likely he will do just fundraising. Okay, now you know that in the case of Democrats and Republicans, right? California is a heavy Democrat state. Texas is heavy Republican state. So actually, in both cases, Biden, Mr. Biden will not come to California to campaign. Why? No need. He is basically on paper, theoretically, and practically already won California. So there's no need for him to come to California to campaign. He may come here for fundraising. Okay, just like Trump will not come here for campaigning. He lost this state even before the election started. Okay, but he may come here for fundraising just to get money from here and apply that, use that in other states. Like Mr. Biden will also may also come here for fundraising, but not for campaigning. Now, they do fundraising. I'm not talking about Mr. Biden only or Mr. Trump only. That's strategy. They use statistics. There are some heavyweight statisticians behind each one of them. Okay, but we as the amateurists statistician, we can more or less understand why they never come here to campaign. Okay, this state already taken, but when they do fundraising here, for what? They need to get the money from this kind of states and bring it to, they call that battle state, a toss-up state, the state in which the P, let's say, between 0.4 and 0.7, for example. Okay, yeah. In that kind of states, they call that toss-up state because they may win, they may lose that state. Okay, now especially if the number of electoral vote from that state is big, then they will go there quite far. Okay, they will put a lot of money there. As I know, for example, it's Wisconsin, usually Ohio, those kind of states. Okay, anyway, from your notes, the quiz 0, some of you already told me, Thomas, I don't really want you to talk about politics. I hope I don't make you get more disgusted with politics, but you see how the application of statistic into this. Okay, so you see how we use stats. It's not about the politics, it's about how stats being used even in those nasty places. Okay, yeah, that's the sum. This is just number, there's no story here, right? Okay, let's do some story. Let me pick questions from our textbook. Let's see, maybe number, the word problems may be too long. Okay, let's do number 28 from 9.1. I'm not sure if I want to do all 5 problems, but let's see. This is number 28. So from here in the Gallup poll, USA Today Gallup poll, we found that 768 of 1,024 randomly selected adult age Ds stated that candidates, oh, okay, that's something to do with voting again. Okay, stated that candidates' position on the issue of family values are extremely or very important in determining their vote for president. Now, I have no intention to go into a presidential election anymore, but just take a look at this from the point of view that this problem is from the book. Okay, so we just do it as a problem, not for election thing. Okay, so let's write down what we have here. The N is 1,024. Okay, and the number of people say that it is extremely important or very important is 768. Okay, now then part A, obtain a point estimate for proportion of adult Americans who say that family values is extremely or very important for their vote. Then the best point estimate is P hat equals to 768 over 1024. 768 over 1024 divides, oh, exactly 34, 0.75. Okay, then part B, verify that the requirement for constructing a confidence interval for P are satisfied. Now, what they want us to show is NP hat Q hat is at least 10. That's what they want us to show. Okay, that's what they want us to show. So 1024 times 0.75 times Q hat is 0.25. Now, I hope you realize that this guy here will give us the number of people say so. That's 768. times 0.25. Is it greater than 10? Is it greater than 10? You can see this is definitely greater than 10. 768 times 0.25 is 190. Right? Now, using my method of computing it, you see that the x is at least 10, at least 5, and n minus x is actually 200 something, right? Also greater than 5. So this is the practical requirement, while this is the theoretical requirement from our textbook. Now the thing is, how do we know that this 1024 is less than 5% of the population? Yeah, we know because the number of people voting will be at least 1 million, right? So 5% of that will be 50,000. So we are fine so far. Okay, so this is a check. Now part C, construct a 99% confidence interval. Confidence level, 99%. So step 1, best point estimate. Please write it again anyway. Best point estimate x p hat equals to 0.75. And then critical value, C critical for 99%, that's inverse norm of 0.99501. As I remember, that's 2.57583. But let me confirm. I don't want to be wrong in this case. Yeah, that's right. Okay, and then step 2, margin of error is 2.57583 times square root of p hat times q hat over n. So we use that number, 2.57583 times the square root of 0.75 times square root of 0.25 over 1024, all under square root. I get margin of error is 0.03485586. So step 3, my 99% confidence interval for P will be best point estimate minus margin of error less than P less than 0.75 plus 0.03486. 0.71514 less than P less than 0.78486. That's for part C. Let's see part B. Is it possible that the proportion of adult Americans aged in this age group say that issue is extremely or very important, the proportion of that is below 70%. Is it possible that it is actually less than 7%? The answer for part D, the answer is yes, it's possible. Because we did estimation, okay? So even our model is not 100% true, okay? However, we have some level of confidence there. We are 99% confident, okay? So is it possible? Yes, that's possible. Is it likely? No, it's not likely. The chance is small, okay? The chance is small. we can say that the chance is actually incorrectly, but close enough. The chance is actually around 1%, actually 0.5%, less than 0.5%. Okay, less than 0.5%. It's like asking me this question, Thomas, is it possible when you buy, today is Wednesday, so is it Mega Million? Yeah, is it possible that when you buy a lottery Mega Million today, you actually hit the jackpot? Yes, it is possible. Is it likely? No, it's actually very unlikely. It's actually very unlikely. Oh, by the way, do you believe that this kind of statement? That's a little kind of like, I don't want to call that I don't want to call that a joke, because it is not a joke. It's not a joke. But side note, side note, uh, uh, which is more likely? Uh, Win a jackpot or hit by thunder? The thunderized, or win a jackpot? Okay. Win a jackpot. Or can get hit by thunder. Oh, I think I say it wrong then. Sorry, not thunder, lightning. Win a jackpot or get hit by lightning. Yeah, it is actually more likely to get hit. No, it's not a game. I mean, in reality, actually, I don't care about the game. We can simulate a lot of game and none of them actually match with the reality, right? Just like the last election, they did the polling and then of those polling, none of them right. Right? So no. But seriously, this is not a game. I'm talking about some reality here. Okay. Now, so let's take a look. Let's take a look on. Give me a second. Let's go to our website. Let me open up my browser. Okay. Let's see. Okay. Most how to say that? The person who won the most jackpot. How to say it? So how how to say that? How many jackpots a person maximum had so far? Most jackpot a person won. That's not what I'm referring to. Okay, who has won the lottery the most time? Okay, so the name of that person is Richard Lustig, the only person in the world that won 7 times in the lottery. Okay, but is that 7 times our jackpot? This is winning lottery, but not the jackpot. Okay, as I know, the number was actually 4. There's one person in England. There's one person in England actually won jackpot 4 times in, I think in her, it's not he, in her lifetime. More than once. How about this one? This is 2 wins. So somebody get 2, somebody get 2, somebody get 2, somebody get 2, get 2. But this is not Mega Million Super Lotto case. 4 times, 7 times. Oh, this one is, no, this is not. I need to read this more. As I know it's 4. Yeah, this person have 16 winning tickets, but it's not the not the jackpot. Okay. You can do your comparison yourself, but hit by lightning odds. Like most times. His name is Roy Sullivan. Oh, what is this? Asking for money, I guess. Sorry, not now. And Sullivan was hit by lightning 7 occasions and survived all of them. I don't know what kind of body he has, honestly. This person can get hit by lightning 7 times and survive. Now, the thing is, because he was recognized by Guinness Book of Records, and the one that we saw earlier was not, right, about the number of jackpot they won. It's not, was not verified, right? So you see that what I want to say is, in the end, is that you are actually more likely being hit by lightning than win a jackpot. Strange, huh? Have you ever heard that kind of comparison? Okay, yeah. I think it has something to do with the fact that lightning is not something you can be, it's not something that makes your life a lot better, right? So that nobody really cares if you get lightning or not, right? But if you win a jackpot, there's a chance that then all of a sudden you have a lot of friends, Facebook friends. And all those people who is your cousins, I don't know how they're, like 7 times cousins suddenly call yourself his or her cousin because you suddenly get rich. Maybe because of that, and then these kind of people cannot survive long enough. Could be. Yeah. No, but we don't know. We don't know. Okay. Yeah, but you can try to find out further. Yeah, you can try to find out further how many times a person hit the jackpot the most. Okay, and as far as I know, the last time I saw was 4 times, and that's somebody in England. Somebody in England actually hit jackpot 4 times, and you can guess that person is very, very old and turns out to be not that rich, because what he or she won, he or she spent it back to winning the lottery, to playing, buying the lottery ticket, and basically spend most of his or her money again, you know. Okay, at least this person survived 7 times. Don't forget, this person, as I know, as I read earlier, still alive. So there's a chance that he get hit again. Okay, now it's actually not about he survived or not, though. The fact that he get hit 7 times and maybe 8 times, okay, we don't know, regardless he survived or not, that's already something. Okay, yeah, that's already something. Well, anyway, that's a little side note. Yeah. So when I say to somebody this question, Thomas, do you think I have a chance to pass this class when my test score is only, my test 1 score is only 10? If your question about is it possible, the answer will be yes, it's possible. Is it likely? The answer is no, it's very unlikely. Why? The conditional probability, given that your test 1 is that poorly done, what's the probability that your test 2 can improve by 6 or 7 times higher? While it is possible, it is very unlikely. Okay, so everything is possible until you start quantifying it. So one of the things probability and statistics doing is actually put the number into what we call an event. And from there, you measure if there's a risk that you are willing to take. you know. So yes, you can call that gambling. You just don't use money. You just use other things, your time, your effort. Okay. So Thomas, are you telling me that I should drop the class? No, 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 not at all. In fact, I have some students asking me this question, Thomas, with this kind of poor performance I have, should I drop the class? If you are taking this class just to pass this class, then the answer is yes, drop the class. Okay, but the way I see is this: you already spent some time here, you are not doing well, but if you think you can study more and try to catch up, not to pass this class, but just to learn, such that the next time you take this class, you can do better, if possible, get that A, get that B at least, right? Instead of a C when you repeat it, then that would be worth it to stay. Okay, so again, if your purpose is only to pass this class with low performance, then I would say drop the class. Okay, but if your purpose is actually to learn, regardless you pass or not, okay, then just learn anyway. You see? Okay, just stay, and then the next time you take it, you hopefully then you can pass with an even better grade. But for now, at least you learn something. Okay, what do you do anyway at home? If you're not going to work, okay, if you have extra time to actually study, why don't you just study? Okay, you don't, if you drop the class and you end up just playing games, for example, doing nothing at home, I would rather you just keep the class. Okay, I would rather you just keep the class. Even if you say, Thomas, I work part-time, and do you still have time to study at least like 2 or 3 hours every day, you know, call that pay in advance what you're supposed to study for next semester when you retake the class. Okay, yeah, but anyway, that's my personal opinion. That's what I did in the past. Okay, saying that I never failed a class is actually, well, actually I never failed a class. I did drop the class. Okay, I did drop the class, but I don't drop right away. I wait until last minute, then I drop the class, because according to the rule, once you drop the class, you cannot attend the class. Okay, so for me to keep the class, I keep on attending, study as much as I can, knowing very well that eventually I will drop this class, but next semester I will show you what I can do. That's what I told my teacher. Okay, so I hope you have the same mindset. Okay, unless you are so occupied, you have some family issue, health issue that you need to take care. And of course, those are more important than just a statistic class. I mean, stats class is something you can take next semester. Okay, stats class is something you can take next semester. But if your family issue, if you have somebody that you need to attend to help, or you have financial issue that you need to work right now, then yes, that's more crucial. That's more important for this time. Go for it. Okay, and if I were in that case, I will not tell myself that I dropped the class because I failed. No, it's just like I have too many things. I have too many things on my plate, you know, and I just happen to be overwhelmed, and that's normal. That's human. Okay, and if you then choose to drop the class, it's totally fine. Okay, and I will not feel guilt. I will not feel guilty with that. I will not even think that I already wasted my time. No, no. There's always something we can learn from every situation. Okay. Yeah. So that's for part D. Using the result from part C to construct a 99% confidence interval for the proportion of adult ADHDs. For the issue of family is not extremely or very important in determining the fault. So they try to reverse the question. So find 99% confidence interval for proportion of those adults in that age group. Uh, uh, which family values uh, not extremely I somehow think they're supposed to use the word nor instead of just or. Nor very important. But I'm not teaching English, so I'm not sure if I'm supposed to use or nor here. Now then, how do we answer this? You take the 1 minus those numbers. So it will be 1 minus 0.78486 less than P less than 1 minus 0.71514. Okay. By the way, I don't need you to answer it to me, but answer in your heart. Whom of you say family value is not extremely nor very important in their vote? I believe the answer is none. Okay, but I believe the answer is that everybody will see that as important. Now the thing is, the scale of priority in our life. Okay, is family value comes first or second, or is family value comes in number 5 or number 6? Okay, now that's where this statement may become biased. Okay, because the reader, if you don't think about that as if that family value only, if you look at family value only, do you consider it important or not? Of course, everybody will say it's important until you start comparing that with, for example, so which one is more important, family values or health? You see what I mean? Right? Family values or finance. Just like the discussion that we have a lot right now is about which is more important, our economy or the health. So for those people who say that we need to, health is more important than economy, then they are the one who actually support for full lockdown. Okay, and those who are for economy, they are the ones supporting the no lockdown and just open the economy. Okay, but most of us, very likely you and me, are actually somewhere in between. Health is important, economy also important. We try to balance it. Okay, that's why yesterday or 2 days ago, we get lockdown 2.0 for LA County. Okay, but it's not as strict as the one we had first time. Right now, they allow dining outside. Regardless, including me, regardless I agree with that or not, I believe that's actually a form of compromise being taken by our governor and also our mayor to actually balance the need of both. Right? So we keep the spread low at the same time. The economy is not tank. Okay, it's not fully down. That's the case we have right now. So if we only look at that, be very careful with the way things being labeled. Until you think about it, like how can somebody say that family value is not important? Is that person crazy? Until you say, oh, you know what? Well, family values compared to other things like finance, our financial situation, you know, okay? So suppose, for example, if my mom told me, Thomas, I need 100,000. I need $100,000. But at the same time, I'm still paying for my house. Will I say yes or no to her? Will I go to the bank and borrow $100,000 and let her use it? But doing so will jeopardize me, my wife, and my children. Right? Speaking about family values, actually this is my family values with my mom, but Thomas, you can marry again, you can have more children. Okay, but no, but still there should be some balance in there. Okay, mom, I can help what I can, but I don't want to risk. I don't want to take too much risk into my own family, like my wife and my children. At least my wife is someone I already vowed to actually support with my life. I never do that to my mom, honestly. Right? Okay, so that's about balancing. Okay, now right now it's 9:07. Sorry with my lot of story time. We come back at 9:17. Okay, is uh, by the way, I just give you one example on how to apply the template, and yes, you will see this kind of question in my test. Just for part C though, I usually don't ask you. I usually don't ask you to verify the requirement. Okay, I usually don't ask you to verify the requirement here. Part B, of course, part A is basically step one in our template, right? Okay, but yeah, I usually don't ask you to verify the requirement. In your department final, however, they may ask you to verify, or they may ask you, can we use this model? And your answer will be yes, because this requirement is being verified. Okay, yeah. Now, let me spend more time on some conceptual foundation. Couple things to answer. Big notes. First one, what does it mean? Does it mean to be confidence level? Okay, two aspects. First aspect is about quantifying confidence. So when we say, are you confident that this lady or this guy is the person that fit to be your spouse? And when you say confidence, it could mean everything more than 50% in our daily life. Okay, but in statistic, when we say confidence, it actually refers to 95%. Okay, when we say confidence in statistic, it refers to 95%. So the terminology, this is not being introduced in our textbook, but in practice. Confident refers to 95%. When we say very confident, it refers to 98% at least, but usually 99%. Okay, 90% confidence level, it's referred to the phrase somewhat confident. Somewhat confident. Okay, so when somebody asks you, are you confident that your prediction or your analysis is correct? And when you say confident, it refers to 95%. Okay, not referring to 70%. No, no, at least in statistics. Okay, so if somebody asks you how confident you are, then you need to go further. Are you talking in statistic term or just practical daily life term? Because 70% in statistic is not confident. Okay, it's not categorized to be confidence. The probability that you being wrong is actually more than 5%. Okay? Okay, until we quantify something, then this term becomes too, I don't want to call it absurd. It becomes too ambiguous. No, it's not even ambiguous. It has too much room to have mischaracterization. It's like when we say what is confident for me means something different from what is confident for you. like when you talk to me, how confident you are that you're going to pass this class. And when you say confident, for me, it's 95%, while for you, it may be 80%. So what statistics trying to do is to put some number in front of that that has some meaning, okay? And therefore, we can do some comparison later on, okay? That's one. It's about quantifying, and of course, in statistic again, in practical statistic, when somebody say we are confident that the proportion of people who will vote for Trump in state one is between 30% to 40%. When they say they are confident, it actually refers to 95%, at least. Okay, at least. No, when they say confident, it's 95%. I should not say at least. Okay, when they say very confident, means it's at least 99, but most of the time it refers to at least 98, but most of the time it refers to 99%. Now, our textbook do not use this terminology. Okay, and every time I give you a test, when I give you question, construct the confidence interval, when I give you a test and ask you to construct confidence interval, I will always give you the confidence level, okay? But in case no confidence level provided, in case for one question I forgot to give you the confidence level, then by default, use 95%. Why times? Because the word confidence refers to 95%. In case no confidence level provided, then you by default you use 95% confidence level. Okay, now, that's the first aspect. When we say confidence level, we try to quantify the confidence level in terms of numbers, instead of just saying confident, very confident, and it turns out that we have different interpretation about those numbers, about that term, confident. Okay, so when I married my wife, I was quite confident, and it was at least 95% that it will be successful, that we will be okay. I'm not saying that we won't have trouble. Actually, trust me, every week we have argument. Okay, but as a couple, it's more about our ability to settle our differences together and move on. Okay, and yeah, you know, we have differences. Me and my wife have differences, but despite those differences, we still happy to be a married couple. Okay, the second aspect, and this is actually the one being asked in a lot of problems in our textbook, and our department final asks that also once in a while. So when they say, for example, 95% confidence level, once they quantify that, what does it mean? What, for example, what this means? Okay. Now, our textbook strictly warn us against, textbook correctly warns us against saying 95% probability that the parameter in this case population proportion for today, mu for yesterday, to say that 95% probability that the parameter P or mu is in that interval. That's not what it means. Okay. The correct interpretation is when we say 95% confidence interval for P is let's say 0.33 plus minus 0.04. Let's say I just make it simple like that. It means we have confidence, we believe in the procedure. We believe in the procedure. We believe in the procedure that if we repeat this procedure many times, (95% of the will include the parameter. So when I say we repeat the procedure many times, it means we take samples again. Okay, so we do the sampling, let's say 100 times. So you will have 100 different samples of, let's say, if we look back to our previous question here, let's say this number 28. They sample 1,024 people, right? They sample 1,024 people. Now this is only one sample here. Okay, from this one sample, they get this confidence interval. Okay, now you can repeat the same procedure. You take another 1,024 sample, okay, and see how many people say yes to that family value, and then you do this confidence interval again. Okay, you will get different confidence interval, of course, right? Okay, but when you repeat that procedure many times, right? So you will get many samples of 1,024. Okay, then 95%, in this case, 99% of the time, your interval will include that P. Okay, so we don't say the confidence interval resulted has 95% chance to be correct. No, it's about the procedure. Okay, the procedure, if we repeat it many times, then 95% of the resulting confidence intervals will actually include the mu, or will actually include the P. Okay, even though it is actually arguable that these two are actually related. Okay, but our textbook, just like a lot of instructors, including me, warn you against saying that 95% chance that our interval includes that. Okay, so our textbook actually gives this kind of illustration. Our textbook, if you give us this illustration, let me spend more time here. Let's say the mu or the P is actually here. Now then, some of your confidence interval may be here. Let's say this is a number line. Let's say this is a number line. Okay, let's say this is a number line. And let's say the P is actually 0.37. Okay, now then sample 1, you get interval from 0.2 to 0.4. And then sample 2, you do another same sampling with the same size, but the different way, different sample, you make an interval like this. And another sample get an interval like this, But eventually, you may get an interval that is actually not including that mean. Okay? But using that procedure, if you repeat that procedure many times, so you take a lot of samples of size, let's say 300. So sample 1 have 300 the sample size is 300. Sample 2, you have sample size of 300. Sample 3 also sample size of 300. And for each samples, you do confidence interval. Okay, then if you do enough, then 95% of them includes the actual mean. For example, if we say confidence level is 95. Okay, so there's a chance that the sample we get happens to give us confidence interval that is not including the mean. Okay, and the probability for that to happen is 95%. The probability for that happen is actually 5% if the confidence level is 95. Okay, now that one is actually hard to explain. You need to put some thought into this. Okay, now I actually wanted to go to 9.3, but one more topic. This first topic is about what it means to be confidence level. So first is about quantifying the confidence level. That's the aspect that our textbook didn't really mention, or if it does mention, it doesn't really mention it, emphasize that. But it's important to quantify the word that may have different meaning. So when we say majority, majority students at WLAC College is Black and Hispanic. That's true though, okay, the majority. But when I use the word majority there, it doesn't mean it's more than 50%. Because when I say majority is Black and Hispanic, and it means more than 50%, Black is more than 50%, Hispanic more than 50%. When you add them up, it's already more than 100%, doesn't make sense, right? Okay, so when I say majority there, it refers to the top two backgrounds or races that is the most at West LA College. Okay, at East LA College, for example, the majority is actually Hispanic and Asians. Okay, now then the thing is, in our daily life, when we hear the word majority, we may associate that right away to more than 50%. So it has to be seen from the context. Okay, so the phrase that majority of students in Thomas' class is not passing the class, that may mean something else. Okay, in this case, yes, it's more than 50% is actually not doing well. Not only in this class, but in all my classes actually. Okay, I'm sorry, but that's my situation. Maybe I'm not a good teacher. Okay, but the students that I taught actually doing very well in university level, that's why they keep me. Okay, and those students who actually doing well in some teacher's class, when they transfer, they never graduate. So you tell me, what do you want? Okay, but you cannot have it both, right? It's hard to get it both. It's hard to get it both. It's not doable, it's just harder. Okay, and I choose to be a good teacher that I pass those students who can actually survive in the next level. So in my class, I also train you how to be a good student, basically. Well, anyway, coming back here. The second aspect is the interpretation about what 95% or 99% or 98% confidence level means. Now, the other subtopic, and this is the ones I usually ask, is the minimum sample size. Minimum sample size. The minimum sample size required for a sample a given confidence level, given the what's that, given the population standard deviation or sample standard deviation, and given a margin of error. Then what is the minimum sample size? Suppose somebody tell you, I want confidence level 95%. And then my population standard deviation is 2, and the margin of error I can tolerate is, let's say, 5. Then what is my sample size? Okay, what is the minimum sample size I need to take? The formula is given by n equals to the ceiling. We have this notation before. The upper, the next integer of the critical number squared times sigma squared over margin of error squared. Okay, that's if the sigma is given. Now, what if the sigma is not given? If sigma is not given, we then use S, then the minimum sample size will be the first step. The first step, we use Z first. In fact, our textbook only used step 1, but then actually from 1, then you need to do adjustment to get the T critical. Okay, we need to adjust to get the T critical and use that T critical into that formula again. And do step 2 repeatedly until no change in n. Okay, I will do example on that later on. But how about if given confidence level and margin of error for P? Okay, then n equals to critical value squared times P hat Q hat over E squared. If P hat is given, if P hat is not given, use P hat equals Q hat equals 0.5. Now, more part that is not really in our textbook. If P hat is given in interval, use the value closer to 0.5 or 0.5 itself. Okay, now let's explain this. Let's explain this. Suppose, for example, like what I did up here. what I did up here. Let me last week. Okay. Okay. Suppose find the minimum sample size. The minimum sample size required for 95% confidence level, knowing population standard deviation is 2, margin of error 5. Then we will use this. Notice that we know the population standard deviation, right? So it will be critical value equals to inverse norm 0.97501. That will give me 1.95996, I believe. And then the minimum sample size will be 1.95996 squared times population variance, that's 2 squared over margin of error squared. Oops. No, the margin of error usually a lot smaller. Let me change this margin of error becomes 0.5. Okay, 0.5. So this will be, then you use your calculator, 1.95996 times 2 divided by 0.5, all of them squared. I get the ceiling of 61.46 something. And because it's the ceiling, I need to round it up. That's the minimum sample size. Okay, so what if we change the problem a little bit? What if we need n with confidence level 95%, but the population standard deviation is 2. I'm sorry, sample standard deviation is 2. So that's the change. I change that becomes this. Okay, and then the margin of error is 0.5. Now, because we have less certainty, we don't have the population standard deviation, we only have sample standard deviation, then what will happen? What will happen is this, we will do part A1, which will give us basically what happened part 1. What I mean by part 1 was basically what we did up there. Okay, which will give 62. Now the thing is, because we don't know the population standard deviation, we're supposed to use T distribution. We're supposed to use student distribution. But student distribution requires us to know the sample size while we are looking for sample size. So what happened then, we will use this 62 as a temporary sample size to update our C score becomes T score. Okay, so T critical, our T critical now becomes inverse T 0.97561. Okay. Let me use my calculator to find that. I get 1.99962. I get T critical equals to 1.99962. Then I plug this number into the updated minimum sample size. 1.99962 squared times 2 squared over 0.5 squared. Okay, we will only stop when the n that we get earlier, which is 62, is the same to the resulting n right now, which is also 62. So if it is also 62, then we are fine. Okay, but the number is supposed to increase. Okay, the thing is, will that increase significantly? Did you get 61 from the unrounded n? No, the 61 is actually, the 61 here is the degree of freedom. Degree of freedom, which is the sample size minus 1. Okay, the sample size we get in part 1 is 62, right? So the degree of freedom is 61. Now let's see, I continue from this 1.99962 times 2 divided by 0.5 square root. I get 63 point something. So I get 63.97 something. Therefore, I will need to use 64. Okay, now notice that 62 now increase becomes 64. Then you repeat the procedure. Repeat the procedure. Okay, then T critical inverse T of 0.975, but the degree of freedom is now the degree of freedom is 63, right? Okay, and T inverse T, let me see. This time I change it to 1.99834. 1.99834. 1.99834. Then put that into that formula again. If we get the same number, then we can stop. In my opinion, we will get the same number. Now, the second procedure that we do more than one times here is something not in our textbook. That's not in our textbook. I get 63.89 something. Therefore, I still get 64. So, since the updated critical value gives the same n, then we can stop. And the minimum sample size is 64, not 62, not 62 that we get originally. But if you take a look in our textbook just does that one. That's because I try to make it easy for you. Okay, but the 62 you get is being used to update your critical value, which originally they use standard normal, then supposed to be updated becomes T distribution. Okay, yeah. Because T distribution depends on degree of freedom depends on sample size, while we are looking for sample size. So it's there's a circular notion there. For that to happen, that we can settle both cases, find the n by using the n, then we do this by iteration. We do it a couple times until the picture fits. Okay, and that's why we repeatedly do step 2. We repeatedly do step 2 here until there's no change in n. Okay, that's the example. Now, how about when we are estimating p? Suppose, for example, we want the confidence level of 95%. Okay, and from the past experiment, we found that, let's say, 0.3, 30% of students actually taking math classes in each particular semester. Okay, so that's the result from the past, let's say, and find minimum sample size. P to for us to construct the confidence interval for that P, the minimum n, sorry, the minimum sample size. N. And the formula will be n equals to, oh, you know what? Before that, I need to get the critical value first. The critical value, let's see, critical. Remember, that's for P, right? For population proportion. Population proportion, we always use standard normal. Okay, that's inverse norm. (0.97501), and that will be 1.95996. Then plug into the formula 1.95996 squared times the P hat times the Q hat over, oh, I forgot the margin of error. The margin of error, let's say, is we want the error to be 2% or less. So the margin of error will be 0.02 squared. Okay, so this is P hat, this is Q hat, this is the margin of error squared, but don't forget it has to be in decimal instead of in percentage. Okay, and then when I compute this, let's see what I get. 1.95996 squared times 0.3 times 0.7 over 0.02 squared. Ooh, that's 2016.7 something. But this is ceiling, so I round it up all the time anyway. Even if the result were 2016.1, I still round it up. Okay, now let's modify the question. What if the P hat is unknown? If P hat, so let's say in the past we don't have any estimate. If P hat is not given, then we use P hat equals Q hat equals to 0.5. Okay, therefore, consequently, then P hat Q hat is, the product will be 0.5 times 0.5 times 0.25. Therefore, you will see some textbook says that basically, if you don't know about P hat, therefore, you will replace this expression here. You will replace this expression here by 0.25. But that's because the p hat is 0.5, the q hat is also 0.5. That's the reason. Okay, go back to that formula. So the minimum sample size in this case will be 1.95996 times 0.5 for the assumed p hat, 0.5 for the assumed q hat over 0.02 squared. I'm sorry, I need to have a square here. This number should be greater than what we have earlier. I get 2,400.9 something. Therefore, I always round it up, becomes 2,401. So let's see, you see that this extra information 0.3 here, actually helps us to reduce the sample size needed. Okay, it helps us to reduce sample size needed. Now, suppose on the other hand, this case never show up in our textbook, and as I remember, never show up in the department final, but it did show up in my test because it showed up in some university level statistics class. Suppose they tell us that from the past estimate, okay, they found that the p hat is between 0.3 to 0.4. So if they say p hat is from the past experience, they found out that between 30% to 40% of West LA College students take math class in that semester. So the p hat is between 0.3 to 0.4. The rule is if they give you an interval, then use the number closest to 0.5. The number closest to 0.5. So in that case, I will choose 0.4. Okay, use p hat equals to 0.4. Okay, now suppose they say p hat is between 0.6 to 0.9. 60 to 90% students taking math class in a certain semester is between 60 to 90%, then in that case, you will use the one closer to 0.5. Use p hat equals to 0.6. Now, what if it's between 0.4 to 0.6? Use the one closest to 0.5, and in this case is 0.5 itself. Okay, try to imagine this. If you have 0.4 here and 0.6 here, now use the number closest to 0.5 in that interval. And 0.5 will be the closest one. Okay, but you still use the same formula, which is n equals to the critical value squared times p hat. So you see that this is actually the template, the minimum sample size template. Okay, notice that, remember that originally the formula supposed to be, I still have 2 minutes. Originally the formula supposed to be, let me use green there. Originally the formula supposed to be C critical squared sigma squared over margin of error squared, right? That's the original formula. Notice that in our procedure, we actually change sigma becomes the square root of p hat q hat. So what do we replace sigma squared by? P hat q hat without square root. So this is the basic formulas. Because of modification, it becomes this formula. Okay, that's basically what we need to do. Let me see suggested homework from our textbook. So tomorrow I will do 9.3 and start chapter 10, but it becomes very, very crucial tomorrow. I spent too much time actually on this 9.1. What question should that be? Number 11 for to number, I think to number 31 or 41. 11 to 41. Did I say 11? Yeah, 11 to 41. 11 to 41. Do every other odd is good enough. Okay, but feel free to do more problems. I say every other odd here, but if you see, oh, you know what, this question seems to be interesting, then just try to do it. Okay, then just try to do it. Now, what I plan to do tomorrow is 9.3. Tomorrow, I will do 9.3. This is in my test, in my old test, and of course in yours also. But as I was told, actually last semester, that not in the department final, not in department final. The thing is, I don't know if this summer we will use department final or use my final. I prefer my final. Okay. But if the department say I need to use department final, then so be it. But if they say not, we will use department final, it means 9.3 will not be in the material for that final. Okay. Well, anyway, so tomorrow I will do 9.3, and then I will do introduction to hypothesis testing. Now, the thing is, for your 9.3, I need you need to have programmed your calculator. For inverse chi-square distribution. Inverse chi-square. See the YouTube link. See YouTube link. Link on yesterday's discussion board. Yesterday's discussion board. When I say discussion board, is the place that you keep on typing here, you know? Okay, yeah, but take a look on that discussion board. You will see the link and program that. Okay, that's for today. See you then tomorrow. I have one